Hello to everyone, and on behalf of the IRENA Online Seminar Committee, I would like to welcome you all to the first IRENA seminar of this year. You all know that from September to the end of the last year, we had a very successful program. And of course, this tradition will surely go on also this year. We have already fixed the next seminars for this semester, and I would like you to remember that the next one will be already in 2 weeks, the 3rd of February already, the same time. And now I don't want to take so much time to Professor Diehl. Let's move to today's seminar. I am very pleased to welcome our speaker, Professor Ronald Diehl from the Max Planck Institute. Now he's sharing the screen, so it's perfectly working. Professor Diehl got his PhD in 1988 in physics and astronomy at the Technical University of Munich, and spent, I would say, the rest of his career in high energy astrophysics and nuclear astrophysics. I will not go through his very long and amazing career, otherwise we will need probably these 2 hours to discuss his career, and we don't want them. Today he will discuss with us the challenges in the context of the nucleosynthesis sources and the properties of our galaxy. Now I will just remind some issues. First of all, I hope that you all will enjoy the seminar as I usually do with his talks. As you know, we welcome you all to ask questions. We asked before to Professor Diehl if he wants to be interrupted during the seminars, and of course he agrees. So please, if you have any question during the seminar or at the end, you may write them down in the chat and we will let him know. I also wanted to remind that as all the seminars is being recorded and will be uploaded in the YouTube website. And the last thing that I want to remember is that after the discussion, we will meet in the Gather Town, when you can also have some unofficial questions to Professor Diehl. And with this, I welcome again Professor Diehl and enjoy the seminar.
Thank you very much for this kind introduction. I'm happy to be the first speaker of this seminar series again, and let me wish you all a happy new year. And we'll start this series with a talk which is basically an observational talk, but as you heard before, I have been working for almost 4 decades in that field, and I started with constructing gamma ray telescopes in the early part of my career after having studied nuclear physics in Mainz. And today what I want to do is I want to share some insights from you from those many years learning from gamma ray spectroscopy with different types of telescopes. I'll first introduce the science context a little bit, and then I'll talk about the instruments briefly, some characteristics. And then I'll pick 2 examples of what we have been learning so far, and I will go through that in some detail and summarize. So let me begin by reminding you that the main theme of my work has been cosmic nucleosynthesis, and these 4 groups of different types of nucleosynthesis should be distinguished because they operate in different parts of the cosmic evolution. There's first the Big Bang nucleosynthesis, and then there's nucleosynthesis that drives the existence and the endurance of stars. Then there is nucleosynthesis during stellar explosions. And finally, there are some high energy collisions with cosmic rays that lead to spallation nucleosynthesis. When you look at the characteristics of all of the nucleosynthesis reactions, they are driven by the binding energy per nucleon being different for different nuclei. So the light nuclei like hydrogen and helium have lower binding energy per nucleon than, for example, iron-56, while for the heavier nuclei, the binding energy then per nucleon goes down again. So you can gain energy by fusion up to iron-56 or by fission from the heavier elements fissioning down to the iron group. In all cases, we have rearrangements of the bound nucleons by nuclear reactions. Now, the crude picture of cosmic evolution is displayed in this little bit complex chart, and you see the arrows on the right-hand side. There is this gray time arrow that goes from the Big Bang, where the composition essentially was hydrogen and helium, as you see in the top part. Maybe you see that up here. And today we have the great variety of different elements that are shown in the bottom left part. And the arrows on the right-hand side, they show what the most important sources are. And we have by far a dominance of core-collapse supernovae and massive stars. And then we have a few other events that are important for some of the elemental abundances. And all of that happens since the Big Bang. And the solar system, for example, has been isolated some 4.5 billion years ago. But today we have still nucleosynthesis going on by all those different types of sources. The massive stars were the first sources, and later sources that are related to binaries started to catch it. The process that we believe happens in any galaxy like in ours is that stars are being formed out of the interstellar medium from the dense parts of molecular clouds. And those stars then they evolve during their lifetime, which depends on their masses. And at the end of their evolution, they will return some part of the mass that has been enriched with a little bit of heavy elements into the interstellar medium. And this is what's called the cycle of matter. And dependent on the mass of stars, the more massive stars, they develop much faster and they return material after a few million years, while the lower mass stars take more time for that. And all of this mix of evolution then is what we try to understand. And we try to model this. And this is a description of how chemical evolution models try to trace what happens during this process of chemical evolution. This starts from a continuum equation of the mass of gas and stars, and how the gas mass is turned into stars and then brought back into the interstellar medium. And there is some exchange with external material from outside the galaxy. So there is some blowout and some infall from the intergalactic medium. That mass flow is changed by gas that is ejected from stars, and that's the second important component. And there are some time delays dependent on stellar evolution and on binary evolution. So when you form stars, it takes some time to return the products of stellar nucleosynthesis. And of course, we need to know what type of new nuclei are generated in that process. And that's the third component that is essential for such modeling. And of course, you need some details on the different types of sources. So how fast do they evolve? When do they return their gas? How much nuclei of a particular species is returned? And of course, you need to know where does it happen? Where in the galaxy do we find all these different types of sources? So that looks like a complex model. The underlying physics is fairly simple, straightforward nuclear physics, illustrated here, and you're probably very familiar with that. The plasma in cosmic sites reacts different than in a nuclear laboratory, because you have a thermal distribution and only the high-end tail of the very energetic particles will be able to overcome the Coulomb repulsion and get close enough for nuclear fusion reactions. And that creates this gamma peak that typically lies at an energy of 20 keV or so. Now, on the observational side, we have this plot of the abundance of elements versus the elemental charge. And you see in the red dashed line that this abundance distribution has a characteristic shape that is reminiscent of the physics of nuclei, and the physics of stars. You see, for example, an odd-even effect that tells you about nuclear physics, and you see a maximum around the iron group where the binding energy is maximized. You see some double peaks for the R and S processes back for the more heavy elements. All of that is quite informative already, and we try to learn from that. This is it has been exploited since many decades now. And for example, one started by looking at the very heavy elements and tried to decompose it into different processes to try and isolate different nuclear physics components that seem to be easy to handle. And this way you can get some modeling and some observations of elements and of isotopes. And that's one way to try and break down the complex problem of all those different source varieties into the more simple parts, assuming that you can isolate such processes that operate homogeneously over the entire lifetime of the universe. Doing things like that, this is the textbook picture that I took from current literature, from Andy Davis's graph, showing that you can distinguish the different processes even in the elemental abundance distributions. And of course, the underlying physics is then properly dealt with in the table of isotopes that is shown in the main part of the diagram, showing the different processes that we try to isolate from each other and try to separately analyze. But all of this is happening at the same time. Many, many isotopes are involved in nuclear reaction networks. And so this is the superficial part of nuclear astrophysics that we teach to students, but in detail, this breaks down as soon as you look a little bit more into detail. For example, on the top right, you find one of the recent confrontations of theory, which is the lines in the graph with observations of stellar abundances, which are the black dots. And you see that while for some elements, the dots and the lines match quite nicely, for other elements, for some surprising reason that we don't understand, we find discrepancies that are very significant. So the model is far from being complete. And when you look at the supernova rates and the star formation efficiency that you need for the red lines shown in the upper graph, then there is also a discrepancy. We don't see the number of supernova remnants or the supernova indications that would correspond to the star forming efficiency that we always assume. And of course, for the early galaxy, it's difficult to find how the contribution from rare sources that contribute to our process elements would be properly modeled. And that's shown in the bottom graph of the three upper graphs. And of course, then there's some mixing of stars and gas in galaxy collisions that was only discovered recently with the Gaia mission shown in the bottom graph. And all of that complicates the entire issue as I tried to describe before. And so we really need observations of all kinds to complete that picture. Now, in this graph, I show the different variety of methods that complement each other to try and get observational constraints on the physics that I was describing before. What I am dealing with is the bottom line, which starts from the nucleosynthesis event and the ashes produced out of there. And when you have an isotope that is radioactive, then you get a characteristic gamma ray line that is properly the most direct way of observing a cosmic abundance. It would be nice if we could do that for all the nucleosynthesis events, but you saw that stellar abundances are a far more dominating messenger from astronomy. And if you look at this, then what you find is the ashes are ejected into interstellar medium and somehow incorporated then into a next generation star. And in that star, you have in the photosphere some of that material, and the underlying starlight illuminates it, and that's what the stellar abundances are drawn from. And all the other processes here, they are sort of abundant assumptions in the whole process. So much of our knowledge is taken from more indirect observations like that. On the top part, for example, I illustrated here stardust, which is little materials that are found in meteorites, and they have taught us a lot. So now let's go to gamma rays. This is the part that I really want to show you some details. At present, we have two telescopes in space. One is the Integral mission that was launched by ESA in 2002, and it was supposed to only operate for a maximum of 5 years. And we are now beyond 20 years of operation, and we hope to be able to continue to the end of the mission life to 2029. So that mission I will mainly talk about. There is another mission that is the NuSTAR mission. That's an X-ray telescope that helps with that because its energy range extends a little bit into the range of nuclear lines that you can do nuclear astrophysics with. And what is that range? Well, it starts from energies like a few hundred keV or a few 10 keV in the case of titanium, and goes up to a few MeV. And this list of radioisotope is the basic list that we can work from. We can look at isotopes of different lifetimes and look at their characteristic XR gamma ray lines, which are listed in the fourth column. And the ones in green have been observed. The ones in blue are still to be found. But this is the list that we expect. And I should add that there are some nuclear excitation lines from spallation processes that I have not listed individually because they are manifold. You see that for some of the lines, there are clear identification of source types, but this is the part that we really want to learn about. And so let me talk first a little bit about how we measure gamma rays. When you want to measure a gamma ray is quite penetrating, so you cannot simply absorb it in a pixelated camera that has a lens in front of it, like conventional astronomy. We have to basically use nuclear particle detectors for that. And there are two fundamental ways how you can do that. One way is to have a kind of a tracking chamber or a set of detectors that measure a sequence of interactions of a gamma ray with the detector material. And from that sequence, you then can use the physics and the interactions to try and work back to where the gamma ray came from. We do that since the Compton effect is the dominating interactions. We call these instruments also Compton telescopes, and they record the interaction of one photon event with the Compton scattering, and then you know the arrival direction within the uncertainty of a cone, like is illustrated on the left side of the graph. On the right side of the slide, you see a coded mass telescope. Here, the technology is a little different. You take a pixelated high-energy detector, germanium detectors in the ideal case, and you put those behind a coded mask. A coded mask is basically an aperture that has holes and closures. And this way, you get some imaging information from the shadowing that is imposed by the mask. In both those cases, the loss of efficiency occurs because you either absorb some photons in a mask, or in the Compton telescope case, you require a coincidence among many detectors, which is also quite a loss because you cannot have a 4-pi coverage of all the detectors. And that's why the achievable sensitivity is only at the level of about 10 to the minus 5 photons per square centimeter and second, which is relatively much poorer than in neighboring parts of the astronomical field in the electromagnetic spectrum. The angular resolution from the penetrating nature of the gamma rays is limited also to the range of a degree or so, which is a price you have to pay for working at those high energies. Now, the SPI instrument is the spectrometer on the Integral spacecraft, and it's such a coded mass telescope. You see how a tungsten-coated mask looks like in the upper right graph. The camera is the middle picture on the right-hand side, which is composed here of 19 germanium detectors. And on the bottom, you see the anticoincidence, which is a BGO detector, which has many, many photomultipliers. And on the left-hand side, you see the imaging principle that this spectrometer does, which is the shadowgrams that are cast by the coded mask onto the pixelated detector. And those shadowgrams depend on the direction. And this is the way how you can distinguish different arrival directions of the photons. The spectra of a germanium detector, they look like this. This is a mission-integrated spectrum from integral, going from 20 keV at the low energy side to about 8 MeV at the high energy end of the SPI instrument. And in the inset on the top right, you see a small region around the line of aluminum 26 that I will discuss a little more. And in this inset, you see that there are 3 major instrumental lines. And this is an instrumental line that is right in the area of the aluminum line, and only about 1% or so of what you see here is actually coming from the sky. The rest is all instrumental. And all the lines that you see in the spectrum here, they are about 400. They're all instrumental background lines, and we have to learn how to properly model them to be able to do our analysis. And all of this is made a little more complex because we operate in space, and we have a very violent cosmic ray irradiation environment, which destroys our germanium detectors. And so every 6 months, we have to do something against that. We have to heat them. So normally they are operated at 80 Kelvin, and we heat them up to 100 degrees centigrade for about 2 weeks. And in this way, the radiation damages by the cosmic rays are restored again. We have done that now 39 times, and it seems to work quite nicely, as you see from the mission history of instrumental resolution shown here. The analysis is not simple because you have to use those shadowgrams, and those shadowgrams are a great variety, as you see in the bottom part of the slide shown here. Those are 25 shadowgrams shown for different pointing directions. And then we use the background models of the detector behavior from all the different instrumental lines. 2 different lines with their ratio of the intensities in different detectors are shown here. So this makes the essence of our background models. And the equation that you see basically shows how we analyze the data. We assume a certain distribution on the sky that is called M in this case. Then we fold that through the shadowgrams, and we combine it with a background model, and we have parameters that are called theta in this equation. They are optimized in a maximum likelihood fit to the data. That data are called decay in that case. And that typically uses about 1 million of these germanium detector spectra taken from different detectors at different times and pointings. And all of this is combined in the multi-dimensional analysis of the maximum likelihood fit to then present you with a result. That looks pretty complicated, but this slide here shows that it really works. It shows the result for the aluminum 26 radiation coming from the sky, and you may see the histogram that is shown here in gray that shows the 3 lines that I pointed out before in this inset. This is now reduced by a factor of 5 just to compare it with the aluminum result. And you see that the instrument lines are nicely taken away by this analysis. And what we see is really the sky, and the celestial aluminum line. If you look at it in great detail, the peak position is actually a little bit offset from the instrumental feature. So that works, but I think those slides showed you that gamma ray spectroscopy is not what you do in back of the envelope calculation. You need heavy computing for that. Now let me switch to some results. And I want to start with trying to understand sources of new nuclei. let me start with nickel 56. Nickel 56 is in the iron group, and it is the radioisotope that is responsible for supernova light. You see, for example, on the left-hand side, the optical light curve of a supernova, which peaks about 20 days after the explosion of a star. And the gamma ray light curve, as expected from model, is shown in the bottom curve. So the fact that you see this optical light is due to the fact that the envelope of the explosion absorbs the gamma rays, scatters it down in energy, and re-radiates it as optical light. So the real source is the gamma radiation that comes from radioactive decay that is shown in this decay scheme here. And we were always looking for opportunities to observe this. It took a long time. It took about 40 years after predictions until we had a supernova that was close enough so that we could see it with our current sensitivities of the gamma ray telescopes, in this case of integral speed. And you see on the top left diagram, these are the lines that we have measured from the two characteristic lines. Let me just go back to the decay scheme. And then these are the brightest lines here. They have energies of 846 and 1238 keV. And they have been seen, they are superimposed so that they are co-aligned here. And they are clearly very much broader than the instrumental spectral resolution. They are Doppler broadened by the explosion kinematics. The instrumental resolution is shown by this black line that shows the instrumental narrow line. So we could resolve something like this. We have seen a very broad distribution, and we have seen that the intensity rose with the, like these red data points, it rose and fell again about as expected from some classical models. We could rule out from this behavior already a white dwarf merger model that would rise too slowly compared to what we had observed. But nicely, these lines, they are the first clear direct evidence that the assumption of the nickel 56 as being a source actually is reflected also in the direct measurement of the characteristic gamma rays. And the nickel mass that we have derived is about half a solar mass, which is quite consistent with models of type 1a supernova explosions. Now, I mentioned that our spectral resolution is actually much better than shown here. And when we use that, then this is the 847 line shown in 4 different panels at 4 different times and at 4 different resolutions. So this is the highest resolution column here, and this is a cruder binning, a more crude binning. And you see that if you look at those spectra at different times, they don't look like a broad Gaussian at all. They look like that the Gaussian actually gradually builds up with time when you integrate over the entire 100 days or so of the light curve. When you look for shorter epochs, then you can see individual bulk velocities that look different. So it looks like that the whole explosion may not be as homogeneous as we normally assume that. It does not just reveal a spherical expanding nickel bubble. It may actually be due to some kind of clumps or bullets of nickel 56 that may come out there. And this is only visible with gamma rays, because in the re-radiated optical light, everything like that is integrated over, because you have the absorption and re-radiation that integrates over large parts of this bolometer that is the expanding envelope. Now we have seen in that supernova also some very surprising thing. We have seen the characteristic nickel lines at 2 different energies that only come out early, because nickel 56 decays really rapidly. What we showed you before was the cobalt 56 lines that come later. And the nickel should be totally enclosed in the envelope in the early 40, 50 days or so. So you should not see nickel lines. The fact that we saw the characteristic nickel lines, even though it's only 3 to 4 sigma significance, is an indication that nickel was visible very early on, so it must have been very close to the gamma ray photosphere, which means it must be close to the surface of the explosion. And that tells us that this explosion may be something like a triggered explosion, so a double detonation being due to either two white dwarfs colliding or a helium accretor. The helium accretion scenario was favored by a model that we published in our science paper and is shown on the bottom left. So also from gamma ray observations, we have a confirmation that the type 1a explosions are really not a homogeneous class, but they are a variety, and only with the Phillips relation you can get standardizable candles that you use for cosmology. But in reality, there is a variety of scenarios that can lead to the final explosion, and not all of them are so well behaved that you can use this Phillips relation for the brightness calibration. Now let me switch to core collapses. The supernova 87A was the event that basically dominates what we know about core collapse events, because this is the only one where we were witnessing the explosion and the subsequent evolution to a supernova remnant. And so we can actually trace with modern detectors what happens right after the explosion. And in the later light curve, we see that it's not the nickel 56 that dominates anymore, but it's this purple line here, which comes from titanium emission. So when you look at 10 years or later after the explosion, all the nickel 56 has decayed to iron 56 already. So the cobalt decay also is over. And in the late phase, you have different radioactivities that still keep the remnant from being glowing in re-radiated optical light. And nicely, NuSTAR was able to measure that. And so you see the NuSTAR result on the left part of the slide in the diagram, showing clearly the characteristic lines from titanium decay. And that was another direct evidence of nucleosynthesis of iron group nuclei being responsible for a lot of material that is ejected from a supernova explosion. Now, this remnant is really interesting because NuSTAR had the nice fortunate setting of the source being of such a diameter, of such a size that the field of view was just right to make an image of that. This could not be done for supernova 87A that I showed before. This could only be done for Cassiopeia A, which is in our galaxy at 3.4 kiloparsecs distance only. And there, the situation is suitable for imaging. So this image is a textbook example because it shows the bluish areas of titanium emission being, again, clumpy in nature and not homogeneous. And the titanium emission is actually inside what was imaged from recombination X-rays before, that was known from the Cassiopeia A remnant. So the X-ray image has been a puzzle because the iron that is shown in red here appears to be outside of the silicon and oxygen ejecta, and that should not be according to our understanding of a core collapse explosion. And the titanium emission from radioactivity shows that the X-ray recombination is actually biased by the fact that you need to have the atoms in the proper ionization state to get the recombination radiation. So you need electrons around the atomic nuclei. When you don't have that, then you don't get any X-ray emission, even though iron is probably present in the inner parts where you show the titanium being present. So that led to a revision of our interpretation of the Cassiopeia A images. Now, NuSTAR having such great observations, they could also measure more details. They could resolve different regions of the supernova remnant and show that the kinematics of the titanium ejecta is actually different for different clumps in that region. In general, they saw a redshift that was modeled by Ejecta and others a couple of years ago to show a bulk velocity of about 1,300 kilometers per second, in that case of the ejecta moving away from us as observers. Integral measures also the titanium emission, and the titanium decay is shown on the top left. It again is a cascade decay, which has another line that is at higher energies than what NuSTAR can measure. And since the Doppler effect is proportional to energy, one can see here that the Doppler signature of the redshift is even clearer in the high energy line. Even though the line is not terribly significant, you see very clearly that the lab energy lies above what seems to be the fitted distribution of the measurement from integral. So much about understanding explosions. Now I get to my second example, and that's tracing the flows of cosmic matter. This brings me to my favorite nucleus. It's aluminum-26, and you see here a summary of our observations that we have over the past few decades. The image that you see is taken from the COMTEL mission. This mission is shown on the bottom left. It operated from 1991 to the year 2000, so it's more than 20 years ago, while integral is still going on. COMTEL was good in imaging because it was an imaging Compton telescope that is a little bit more suitable for doing large-scale images than the coded mass technology. On the other hand, COMTEL had an energy resolution of only 200 keV, while integral has about 2 keV energy resolution. And so you see that the discovery spectrum, also from a germanium detector shown here from HEALC in the middle, is improved by integral quite a lot, and we can clearly resolve the line and do some interesting kinematic studies with that. And I will come back to that a little later. I'll show you here that the image from COMTEL is reminiscent of the clumpiness of the appearance of our galaxy when we look for massive stars, like for the OBA stars in the middle, or for the clusters of stars that are imaged by Gaia. And so that took us to believe that massive stars are the dominant sources. But on the other hand, we knew from pre-solar grains that there are very clear signatures from grains that are identified to come from AGB stars and also from novae that clearly show signatures of aluminum-26 enhancement. So here you find two different astronomical messengers. The pre-solar grains, they show you the nova and AGB star signatures of aluminum-26, and the image from gamma rays seems to point to massive stars. So we have a puzzle. Now, when we took the model yields from massive stars and combine that with our interpretation of the image that I showed you before, then I think we can state safely that massive stars are the dominating sources of aluminum-26 in our galaxy, while AGB stars and novae probably contribute at a 10% level. And using that knowledge and the nice spectrum that we have after 20 years of the mission, we have been converting the gamma ray flux into a core collapse supernova rate estimate of about 1.3 per century, or 1 every 70 years or so. This is an independent measurement of the galactic supernova rate. The other measurements that we usually refer to, they are taken from the vicinity of the solar circle, so from nearby OB stars, and there you have to assume that the galaxy at large is not different than our solar system environment, and that's quite a strong assumption. So it's good to have some other observations with other systematics. The gamma rays, they reach us from the entire galaxy and not just from the nearby stars. Now, the ratio of aluminum-26 to 27 can be compared from the gamma ray observations to the pre-solar grains. And there you clearly see that the blue hatched area is the ratio that we have in the current interstellar medium. And the other bars, they show enrichments by aluminum-26 that are much larger, and they just tell us that those grains must have been formed very close to aluminum-producing sources, so that the aluminum-26 component is strongly enriched, and that is consistent with AGB stars and novae being the sources. So that is clearly showing us that we have to look for the biases of each observation to try and understand it. In terms of understanding the origins of aluminum-26, this is a Kippenhahn diagram that shows stellar evolution in a log timescale. So it starts from stellar birth at the left end. And let me show that here. This is where the star is born, and this is the time of the supernova explosion, and this is a log scale in years. So this is 1,000,000 years, and this is the main sequence phase shown here, which is dominated by hydrogen burning. Then you have helium burning, carbon burning, and so on. And the aluminum production occurs in hydrogen burning, and later in some oxygen shell burning, and during the explosion itself. Now, this is the core of the star, the inner part, and this is the surface of the star, and you see the mass loss here brings the products from hydrogen burning, mixes it into the envelope, and that means that aluminum-26 is ejected already from the stellar wind before the supernova happens. If you look at a group of such stars, then you can look at the time history and you can see the same effect. There is my cursor. So here is the evolution time of an entire group of massive stars, and the winds, they start to blow very strongly in the Wolf-Rayet phase after about 2 or 3 million years from the most massive stars, and they already eject some aluminum-26. At the same time, there is ionizing light coming off, and the wind gets stronger and blows bubbles. And so this is what happens in those 3 different observable effects of massive stars. So we can take those observable effects and we can actually model what happens from a group of stars over the course of many stars co-evolving and adding to the interstellar amounts of aluminum-26. So later, supernovae set in, and the supernovae, they also eject some material that is produced a little bit further in. Let me go back to the Kippenhahn diagram. Then you see that iron-60 production occurs deeper in the star, and it has no chance of mixing into the envelope. So this only comes out during the supernova, and that you see in the offset of ejecta being ejected in the circumstellar medium only a few million years later as the supernovae begin to start. So this is a bottom-up theory that we can develop, and we have done that. And so we can look at the evolution of groups of massive stars, and we can, for example, study how different theory inputs would change. And so in this case, on this slide, we have the temporal evolution of the aluminum ejection for different assumptions about the stellar explosions. It's called the explodability. You probably know that not all stars of high mass make a core collapse supernovae. Many of them directly collapse into a black hole. And you can have different assumptions that were made here in the different variants, and then look at how the ejection curves from a group of stars change for aluminum-26 and also for iron-60. And so you see that the ratio of aluminum to iron, of course, changes drastically when you use different assumptions, and we now use observations to try and find out what's right or wrong. We have expanded on such a bottom-up model, building basically from the yields of individual stars, a group of stars first, like I just explained, and then we apply this model to all the known groups that we find in our nearby environment. So we have been using astronomical knowledge about where the massive star groups are, and we put those models at the right locations and with the right intensities, and then use some ray tracing to to try and find how the aluminum appearance in a telescope would look like if we use such a bottom-up model, assuming that we know the nearby locations of stellar groups, and we can take some other model for the more distant part where we don't know the locations, where we use a distribution model that comes also from galactic theory. And with this bottom-up model, we actually have been able to predict an image of the aluminum sky that is shown on the left of this slide. And on the right-hand side, you again see the COMTEL picture. By the way, the SPI picture looks almost the same, and I keep showing the COMTEL picture for no particular reasons, and it's just more common. But those pictures, they look quite similar, and so I would say the bottom-up model based on massive stars only seems to work quite nicely to reflect the morphology of the observations. Now, we also find that when we compare the fluxes over the entire sky, then the bottom-up model somehow doesn't match our observed flux. We see on the order of 1.8 times 10 to minus 3 photons per square centimeter and second over the full sky. And the model predictions are almost a factor of 10 lower. And we have to crank up the star forming rate to an implausibly high value to actually make that match. And so that is a current puzzle. We don't know if we somehow have a problem in modeling the nearby sources properly, because nearby sources cover a large part of the field of view. And since they are nearby, they contribute significantly to the flux. And so observations tell us we have a contribution from high latitudes, which are nearby sources, that we probably have not modeled, not understood to sufficient detail. Now, in the last few minutes, I want to remind you of another aspect of these aluminum studies that are important. We have a germanium spectrometer that has a very nice spectral resolution, so we can see the Doppler shift of the aluminum line when we look in different directions from Doppler motion of galactic rotation. Galactic rotation occurs at a velocity relative to the solar system of only like 100 or 150 kilometers per second, and we can see velocities of that order in gamma ray Doppler shifts, which is quite nice. It's shown here on the right-hand side how the line shifts. And this, analyzing this in detail, has shown us that apparently aluminum ejection occurs into cavities, because we see aluminum moving so fast, much faster than, for example, molecular clouds or other maser sources. And so this excess velocity that is shown on the top graph can only be explained by having a longer time for maintaining the high ejection velocities before aluminum-26 nuclei are decelerated to normal interstellar medium velocities. And that means that the ejection is typically into superbubbles that can be large, like a kiloparsec large. And that has quite some implications for understanding our galactic structure. And we're discussing that with the galactic evolution people. So this is an important part of current astrophysics that we are doing. And this slide here shows the Eridanus cavity, which is a group of nearby stars. And you see on the bottom simulations running of 3 massive stars as they evolve over their timescale of 2 million years or so. And you see that the cavities blown by the winds of those 3 massive stars, they quickly overlap to form what's called a superbubble. And the Eridanus cavity is such a superbubble that is quite near the sun at about extending to a proximity of about 200 parsecs here from the 400 parsec distant molecular clouds and those massive stars that are the aluminum sources. So this region is a laboratory for studying the details of what I showed you before, these superbubble evolutions. And on the right-hand side, you see the bubble walls seen in H1, and these are the CO data from the molecular clouds. Here is the hot Eridanus cavity interior seen in thermal X-rays, And here are the gamma rays from aluminum that shows indications for a blue shift, so that the ejecta are moving towards us as expected from this geometry. Finally, I want to mention a few other things that I don't have time to go into details. We have also seen iron-60 gamma rays. They are shown here in a spectrum together with the aluminum. So this is a spectrum over a broader range showing the aluminum line and the two characteristic iron-60 lines. And the ratio is constrained by some modeling that we have been doing. And it is constrained to being smaller than 0.4 in the galaxy, while theory advocates values between 0.2 and as high as 1. And ocean crust material has also seen iron-60, and there is a lower limit of about 0.2. So these constraints are important for what I showed you on the Kippenhahn diagram before, namely for how is the interior structure of massive stars. Then I want to mention one other thing. I should try and advance. No. Yeah. We also have data with integral on the annihilation line from positron annihilation. Now, positrons are a byproduct of nucleosynthesis. For example, from aluminum decay and from titanium decay, you get positrons also from nickel decay. And those positrons, they must annihilate somewhere. And so we were always interested in that. And we have rich detail because this is a very, very significant line. And you see the image that we have been deriving from integral data and the spectra that are different for the disk part of the galaxy compared to the bulge part. And there is a small region close to the galactic center that again seems to have a different spectrum. And this is also some rich science that is exploited in terms of cosmic ray physics, because those are basically, positrons are part of cosmic rays. We had also seen positron annihilation from a flaring microquasar back in 2016. And this was a very spectacular measurement that showed us that positrons are probably ejected by the jets that come out of microquasars. And this is a measurement of what happens when a black hole swallows material from the inner accretion disk. And it's the first direct signature that is really significant about the measurement of pair plasma being a part of the ejection from such a microquasar. And that's interesting. It shows that those may contribute to the positrons. And if you look at the images that are shown here of our galaxy in different wavelength region, then you see in the middle the positron image, positron annihilation image, and that looks clearly different than all the other images. You see the aluminum-26 image that shows current nucleosynthesis, and you see that those images all are different. They are telling us quite a lot. And so I think observations in the MEV region of gamma rays, they are really important contributors to our astrophysics knowledge. And we would like to have more of that. But I showed you initially that the gamma ray technology is difficult. And so you see in the sensitivity plot over a broader energy range, starting from X-rays to very high energy gamma rays, this region of MEV region is just by 2 or 3 orders of magnitude worse off than all the other regions. In X-rays, the sensitivity is better. And even at high energies from ground-based telescopes, it's better. And that is due to the difficulties that I explained to you. Now, there is integral with the black curve here showing sensitivity currently. It's a little bit better than COMTEL. And we have only one hope, and that's the COSI small Explorer mission that will probably be launched in 2027. That has a sensitivity also shown here. That will be a part of the step that we would be able to do in the lab. This is a full-sized next generation Compton telescope that we would hope to get, but it's expensive and we just don't have the few billion dollars or euros available to have this. And so with this, I'm at the end of my talk, and I put up my summary and take any questions you might have. Thank you very much for your attention.
Thank you. Thank you for the very nice talks.